Alrighty, so complex ion formation relates to coordination compounds, and coordination compounds are a complex structure. They really involve transition metal ions, which are typically colored and often paramagnetic, which means that there's an unpaired electrons in the orbitals, and this creates a magnetic field. And then it causes some differences in orbital configuration with electron configuration. So we'll get into the details of that later, but first I just want to teach you how they are named, and then just the basic descriptions of how the covalent bonding works. Alrighty. In the complex ions, there's always ligands attached to the middle complex ion, which is the central ion. And the central ion, like I said, is usually a transition metal. So if you see silver, often you'll also see aluminum, which is not a transition metal, but it's also included. Cobalt, some coppers. So when you see a transition metal and there's ligands attached to it, the ligands are sometimes neutral. The neutral ones are listed right here as water, ammonia. Chlorides are sometimes not the neutral ones here, and also hydroxides, which are also not neutral. And you'll see that the example list here some of the different ways we'll name them. So aquo, amine, chloro, cyano, and hydroxo. So with our example here, you'll see that there's also counter ions listed. The counter ions are around the complex ion, not part of the ligand structure. And if you have a cation or a positively charged complex ion, you'll have an anion serving as the counter ions, which counters the charge, and that creates your neutral compound. And so you can see here, maybe these right here on the outsides of this structure are the complex ions, and it's also attached in the middle. So they're also shaped very differently. So the reason that we have these ligands are due to the fact that we have to know what Lewis bases are, and so Lewis bases are lone pair donators, and so your electron pairs are going to be donated, and when you totally donate an entire 2 electron pair, we call that coordinate covalent bond. So that's where we get the word coordination compounds. So you're sharing, so they're also called covalent bonds. And so you'll see that over here, you've got 2 electrons that are shared here, 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 here. So it's all based on the fact that you've got 2 electrons to share in the outer shell. So the T metals, or the transition metals, are going to act as the Lewis acid, and the donors, or the ligands, will act as the Lewis bases. So we've just got electrons being shared here. And so with the transition metal, that's going to be accepting it. The reason it accepts a lone pair is because it's going to create a full D block, or D orbital, because the extra electrons fills the orbitals that are not filled. So this is right here is an example of BF3 plus NH3, and so the electron pair from ammonia is being donated, and as it is donated, it's actually forming a new covalent bond. And since ammonia donated both of the electrons, not just each of them are sharing one, that's why you have this coordination, or coordinate covalent bond here. So with the coordinate covalent bonding, like we just stated here, there's extra details. It's usually just, like we said, 2 electrons are donated from the same atom to create the covalent bond. It's different from just a simple covalent bond where each atom or each element is going to be supplying 1 electron for the bond. Alright, so we also have to talk about the number of ligands. So with the number of ligands, it's just you need to know the coordination number is equal to the number of ligands attached to that central T metal. And usually it's not going to exceed 6. So the easy way to determine this is that the coordination number will be 2 times the oxidation number of the metal. So aluminum, which has a 3+ charge, could possibly hold 6, which is the top number of ligands. Copper, which has a 2+ charge, would hold 4 ligands. Silver, which is a 1+ charge, probably will hold 2 ions. This is just usually will occur, but the rule does not always apply. And when you are adding up the net charge of the coordination complexes, you just make sure you include the charges of all metal metals and their attached groups so that you can have the net charge, which is the overall charge. Okie dokie. So we've got this compound here. We've got a nitrogen 2 plus ion, and we've got oxalate ions as well as water molecules attached to it. And so the coordination complexes really do look really weird. And so they're really big. So if we had to name this, if we had to draw it, so here we have the name. We've got the nickel represented. We've got 2 oxalate ions represented, and we have 2 water molecules represented. And I'm going ahead and give you the net charge, and then I'll draw it for you. The net charge is your just 2 of the, 2 plus for the nickel, and then you've got 2 minuses for oxalate, plus 4 just neutral compounds of water, and that's how you get that net charge of a -2. So drawing this one is actually fairly simple. All you do is put nickel in the middle, and knowing that nickel has that 2 plus charge, you've got your chromates, your oxalates that want to be attached here. As well as your waters. And then overall, all you do is, that actually kind of looks like a tetrahedral structure due to the fact that there are 4 ligands attached to it. And this next one is also already named for you, and you've got the tetraamine diaqua copper with the copper 2 plus ion in the middle. You've got 1, 2, 3, 4 amine groups or NH3 groups, as well as 2 waters, 1, 2, and you can tell that those are the amines and or the ammonias and the waters due to the bent structure of the water with the H2O, and then the NH3s with the pyramidal structure. You will not have to draw these, but I was just giving you a couple of pictures of representative of the molecular geometry. So when you actually name the compounds, you have to name the ligands first. So you're naming those attachments first. This is similar to organic chemistry due to the fact you name the substituents or the attachments first, but there'll be some exceptions here. So after you've named the ligands, then you'll name the central atom, which is the transition metal. So whenever you have ligand names that are made to end in O, then they're probably going to be the anions, so the negative ones. So you've got chloro, hydroxo, cyano, and that's the chlorine, the hydroxide, and the cyanide ion. And then you've also got aqua, which is the H2O. Amine kind of sounds like ammonia, so you should be able to remember that. And then thiosulfato, that one's a weird one, but you just have your thiosulfate ion with the O on the end. Ions that will end in 8. These are a little bit more difficult. We'll talk about using the Latin words in here too. For example, you've got your copper and you've got 4 amines attached to it. So since the copper is one that we've also called cuprous, that's the Latin name for it, you'll actually use the Latin name whenever it's attached to an ion. So looking at the example, you'll see you've got tetraamine copper 2. That's just plain old English. But if you've got an anion attached to it, in the cyanide example, you've got hexacyano pulpurate 2 ion. So know that there's just a difference there, but you should recognize both of those as copper. And you'll also see that there's the charge of the copper ion listed at the end. That is something special. You have to signify the charge of this transition metal. And there's another example here with aluminum and the ammonia and the hydroxide, so you can read through that. Also naming, you have to name how many of each attachment or the ligands, and in actually alphabetical order. So you actually will use alpha order. So you've got dibromo here in this example because you've got 2 bromines, dichloro with your chlorine, and you've got diiodo, which because you're 2 iodines. And then finally you'll say, since all of these are anions, you're using the Latin culprit for the copper. And since copper is a 2 here, your entire net your net charge here with 2 negative chlorines, 2 negative bromines, 2 negative iodines, and then a 2 plus copper, that equals to -4 is your total charge, which is the charge of your anion listed here. And then there's another example to signify the copper 1, and you'll see the -4 charge there as well, but you got an amine, which is, or the ammonia, which is neutral. And like I told you, you absolutely have to say the oxidation state of the metal, whether it be copper 2 or copper 1, silver 1, zinc 2. So you'll see the Roman numeral at the end of each name. Okie dokie, so naming is going to be a little difficult at first, but I've given you 9 examples here. I want you to just attempt, remember to name the ligands first, and then name the transition metal it's attached to. And since these are compounds, you'll say chloride at the end, or chloride at the end, or potassium in the front. And that's just because it's an ionic compound. And ionic compounds, you're always going to name the other ion that's also attached to. And then there's some special salts listed here. Just give it a shot, and the answers are actually in the next slide. So take a pause, try a couple, and then go to the next slide. Here are the answers. Check yourself. Read through some of these. These look like they're very, very long and crazy names, but you need to know how to recognize them, and you also do need to know how to name them. So when you see 5 chlorines, you need to say pentachloro. Whenever you see 2 amines, you need to say diamine. And make sure you're in alpha order. Don't forget, you have to put the transition metal charge at the end. So you will probably see one of these on the AP exam. You'll definitely see one on this next exam for AP Chem as well. And there are a couple of reactions that form complex ions, so being able to recognize the key words that could possibly tell you in disguise that you're actually going to be expecting a complex ion or a coordination complex to form, you need to be able to recognize that. So I've already told you that usually for the rule of thumb, you'll have 2 times as many ligands around the ion as the charge of the ion. So with our copper, in this example here, your copper ammonia complex, you've got your copper, that's 2+. And then you've got ammonia, and you've got 4 of them, so you've got tetraamine. So 4 of them, which is signifying your 2 times the number of the charge of copper. So there's a lot of little exceptions here, and I just have a couple of notes here. This is really just a one thing, read through one time. Just follow the naming conventions, name the ligand first. And also, since we talked about acid or Lewis acids and Lewis bases, these are acid-base reactions for the most part, and it's just electrons being donated and accepted. And so sometimes we'll see these with acid-base reactions as well, and just in chemistry. So knowing that the Lewis base is the donor is important. And I told you this in class already, but keywords like excess and concentrated may possibly indicate that you're going to be forming some complex ions. So beware, sometimes those words are really important to notice, and maybe underline, put a star by it so you know what you're looking for. So for example, we've got this excess concentrated sodium hydroxide solution is added to a precipitate of zinc hydroxide. Another word you'll see instead of precipitate is suspension. And that'll just signify the fact that you've had a precipitate or it's in suspension. And another thing that normally happens is you'll see that this double replacement reaction they've given you does not occur. It's 2 hydroxides reacting with one another, and there's no actual double replacement. But whenever you see something and it looks kind of fishy, think about the fact that it could be a complex ion that's forming. So here we do have zinc with the 4 hydroxide ligands being attached to it. So we would call that tetrahydroxo zinc 2, because zinc does have a 2+ charge here. And so since we've got 4 of the hydroxides with a negative charge each, the overall charge of this entire complex ion is a 2-. So I've added just a couple more examples if you wish to take a look. So I've got the net ionics available right here. You've got copper added to ammonia, so then you'll have your tetraamine copper 2 ion. And you know, you can go through and look at the rest of them. Another one is the thiocyanate. We haven't talked about this one as much, but recognize that this is thio. Thio means you've got the sulfur in the front, and it's the cyanide ion. Alrighty, so pretty much in a nutshell, complex ions are possible. You need to know it's usually just with transition metals, also with aluminum, it's a special one. Know how to name. You need to name the ligands first and then the transition metal with the Roman numeral charge, as well as understand that there's a couple of reactions and their telltale signs are saying excess or extra concentrated or in suspension. Or just seeing that you don't think the reaction would actually occur, knowing on the AP exam everything occurs. There's no reaction. So hopefully you can go through your notes and then answer the couple of questions at the bottom of your AP Chemistry Coordination Complexes and Complex Ions worksheet. Let me know if you have any questions.